How to design a bandpass Sallen-Key filter is discussed in this circuit design example. The circuit is implemented with two operational amplifiers, op-amp 1 and op-amp 2, that forms two cascaded stages as shown. And also we have a number of passive components, resistors and capacitors, that we need to find the proper value for them. How does this circuit work in terms of how does it realize a bandpass function? And how can we select the proper value of components? By that I mean the resistors and capacitors in the circuit, so that we achieve the desired transfer function. So if this is the magnitude response, so if the overall system has a transfer function h of s, substituting s with j omega for a steady state sinusoidal analysis, this transfer function, absolute value of h of j omega, is the y-axis here. And if for the x-axis we have the omega, or frequency. So if the target and desired transfer function looks like this, meaning that for frequencies between omega 1 and omega 2, we want the system or the filter to pass input to the output as it is showing. So if the let's say magnitude response for the frequencies in between these two frequency values, they happen to be, if the response is 1, it means that input to output is just passed through for the frequencies that are between these two values. And then outside we start, let's say, attenuating and then ultimately killing the signal. So we want to see for a given, let's say, desired omega 1 and omega 2, what value for the components we need to select. And also a discussion about the transfer function and frequency response naturally. So those are the things I want to discuss in this example. Okay, so let's focus on the first stage, and then we will talk about second stage right after that. Op-amps 1 and 2 are properly biased, so whatever plus minus 5 or plus minus 10 volt applied for both op-amp as supply voltages, it's a dual supply design for instance, and then output is connected via wire to input negative terminal, which means negative feedback is there. So that would enforce op-amps into, so op-amps are in linear region, and therefore the virtual short is valid, which is important for the analysis. So that means the positive and negative terminal have the same voltage. Okay, so we have the same voltage here between these two terminals. Now, the idea, the big picture idea for this circuit is, first stage is realizing a Sallen-Key. It's a Sallen-Key topology. It's realizing a high-pass filter. So as if I show it here, so I'm going to show you the response of the first stage. It looks like this response. So it's realizing this portion. And the second stage, if I show it with different color, let's say if I show it with, say for instance, the orange color. So if this is my second stage, that's another Sallen-Key topology implementation, but because of the way things are wired, we are realizing a low-pass filter here. So it's as if the second stage is taking care of this portion. So then combining in cascade the response of the blue response of high pass and the orange response of low pass, we end up with the overall response that is for the band pass. So by that I mean the overall response that I showed you earlier. So that's how we are implementing the bandpass filter here using these cascade. Let's focus on, now that we understand the big picture, let's focus on the first stage and find the transfer function, but intuitively, so without even writing transfer function, intuitively why this is, let's say, a high pass filter. Quickly, the impedance of cap is obviously 1 over CS for these caps. And when we are doing sinusoidal steady state analysis, then obviously we are substituting S with j omega, so impedance of cap is 1 over jc omega. We know that when frequency is at near DC or DC, denominator is 0, and then the whole cap impedance is infinite. Basically at DC cap is open as known. When the cap is open, positive terminal is grounded, so the voltage at positive terminal is 0. Virtual short forces the negative terminal to be at virtual ground, which means output via this wire is also grounded virtually. So at DC, nothing from input, nothing goes to the output, because output, or the voltage of the midpoint Vm, is 0. So DC doesn't go through the filter. Now, when frequency is high, we have a different story. At high enough frequency, now we have omega going to very large values, so denominator becomes large. That means the whole impedance of cap is going to very small values. So effectively caps are relatively short compared to R1 and R2 values, and therefore we can say Vin is effectively wired to positive terminal directly. So Vin appears here, virtual short enforces Vin to be at negative terminal as well, and therefore via this wire Vm, or the output of the first stage, is also equal to Vin. So that means for, let's say, high frequencies, the first stage is effectively a pass-through. So Vin goes to output directly without any attenuation. So for the first stage, as I talked about, DC doesn't go, output becomes 0, and high frequency at input, so this is Vin, this is Vout. High frequency, actually Vin appears at the output as well, so Vout becomes equal to Vin. So that's a high pass filter. Okay, now that we understand intuitively how the circuit is working, let's now focus on the transfer function. Transfer function is going to be, so I'm gonna delete these, and let's talk about transfer function quickly using a trick. I'm gonna apply a trick. So the trick is, let's say Vm is of course here via this wire, that's obvious. Now, because of virtual short, Vm is also here, Vm, the voltage at the output of the first stage, or voltage of midpoint. We can find this current I1. So I1 is easy to find, which is the same as this current, because nothing goes or coming out of the input terminal of ideal op-amp that has infinite impedance. Effectively, cap and resistor are in series. So I can say I1 is equal to Vm, which is the voltage across R1, divided by R1. So that's good. Let's refer to this as equation 1. Now let's write a KVL, or Kirchhoff voltage law, across these two components in series. Basically, adding the voltage drop across them will give me the voltage at the midpoint, or Vx. So writing a KVL, or Kirchhoff voltage law, I have Vx is equal to voltage of cap plus the voltage of R1, which means the current I1 times the sum of the impedance of these two guys in series. So I1 times 1 over Cs plus R1. Substituting from equation 1 so I'm going to substitute I1. I get 1 plus 1 over R1 Cs times Vm. Great. So I found Vx as a function of Vm. That's what I needed. Okay, let's move on to now writing a KCL here. So I'm going to write KCL at node X. So this node is referred to as node X, and hence voltage at node X is Vx. So writing a KCL at node X. So I have the current that is coming in. So Vin minus Vx divided by the impedance between the two voltages, which is 1 over Cs, equal to the sum of the two currents that are going out, so I1 and I2. Okay, so I1 plus I2. Alright, so substituting for I1 from equation 1 again, here I get Vm over R1 plus I2 is easy, because it is simply Vx minus Vm, the two voltages on the two sides of resistor R2. So I find the voltage drop around across R2, and then I'm going to substitute for that, and then divide by the value of resistor R2. That gives me the current I2. Okay, great. So now let's substitute for Vx. So I am going to substitute for Vx using equation 2 here. So I found Vx as a function of Vm. So I am going to substitute using equation 2. As a result, what I get is, and I can multiply 1 over cs to the other side so that I get rid of the denominator. So Vn minus 1 plus 1 over R1 cs times Vm, that's this guy, and then equal to 1 over cs times Vm over R1, so I can just say 1 over R1 cs times Vm. And then for this one, the interesting thing is we have Vx minus Vm, but Vx is 1 plus 1 over R1 cs Vm. So when we compute the delta, what comes out is simply 1 over R1 cs, and then we have divide by R2 and then divide by cs. So it becomes 1 over R1 R2 cs squared s times Vm. So this is equal. I'm going to move this guy to the other side. So when I do that, then I end up with Vn equal to 1 plus 2 divided by R1 cs plus 1 over R1 R2 c square s square times Vm, the midpoint or the output of the first stage. Okay, so then Vm, so I can say the transfer function of the first stage h1 of s, which is Vm s as a function of s, and divide by Vn in s domain equal to, okay, 1 over, moving this to the denominator, so 1 over 1 plus 2 divided by R1 cs plus 1 over R1 R2 cs square s square. Then multiplying both numerator and denominator with s square to just clean up, I get s squared divided by s squared plus 2 divided by R1 cs plus 1 over R1 R2 cs square. That's it. So what is the benefit of this? Well, we found the transfer function of the first stage. By first stage I mean obviously this stage, from input to midpoint voltage wise, and that transfer function is as nice as this. One further last step to make it nicer is, so I'm going to write it here. I am going to write it with this color. So h1 of s for the high pass filter is equal to s squared divided by 1 plus, I'm going to name this as, let's start from the last one. I'm going to name this as omega n squared, or the squared natural frequency, and I'm going to name this 2 times zeta omega n, where this omega n, as I said, is natural frequency of the first stage, natural frequency, which we will see that it is actually this frequency, so it will be define the omega 1, and the zeta is the damping factor of the filter. So damping factor defines whether we have peaking in the frequency response or ringing in time domain. So I'm going to write it here. So I have s squared plus 2 zeta omega n s plus omega n squared. Okay, in which omega n is, so omega n squared is this one, so omega n is 1 over c square root of r1 r2, and if I just substitute that here, knowing that 2 times zeta omega n is this value, we can compute that zeta, or damping factor, is equal to square root of, so it becomes r2 over r1. So this is the big picture for the, let's say, transfer function of the first stage. What is the benefit of this? obviously you can see when S is going to infinity, which means large frequencies, then it becomes transfer function is dominated by s squared over s squared, which becomes 1 as expected. And when frequency is DC, S is 0, which means the response is 0 as expected. Okay, one rule of thumb, setting the damping factor equal to 1 over square root of 2, resulting, let's say, the flattest or the one of the flattest response in bandpass, so flat response, the flattest we can get basically in band, and basically ends up with having Butterworth implementation effectively of the Sallen-Key topology. Reason for that is just think about set in this equation denominator, think about setting zeta to 1 over square root of 2 and see what happens. So if we set zeta 1 over square root of 2, which is a slightly underdamped scenario, h1 of s becomes s squared over s squared plus rad 2. By substituting zeta with a 1 over square root of 2, we get rad 2 omega n s, and then plus omega n squared. And then if we substitute s with j omega to find the, let's say, magnitude response, you will find, if you just substitute and try, you will find quickly that the response looks like this. So we have, let's say, this kind of a response, omega over omega, or let me put it this way, omega to the power 4, and then we have omega 4 plus omega n 4, which obviously becomes effectively, by dividing both numerator and denominator with omega n, becomes this, which is the standard definition of the Butterworth filter, but the high pass one. So this one, this 4 is equal to 2 times n. N is the order of Butterworth, which means n should be 2. It's a second order Butterworth filter implementation, which has a flattest response in band. So it's sort of a rule of thumb, desired value. As long as we can select it, then it's a good choice. Now, what's the benefit of having this degree of freedom? The component selection, basically, because we are saying, okay, so we set zeta equal to 1 over square root of 2. That sets R1 and R2 let's say relation. So with zeta set to 1 over square root of 2, it enforces R1 to be 2 times R2, so that we get this. So R1 becomes 2 times R2. That's one important relationship for the first stage, of course, for high pass filter. First stage, meaning for this stage. And then by setting omega n to some desired value, so let's say if you want this frequency to be a specific value, then you can find the value of, so let's say if we set omega n to a specific value, given that, for instance, cap is selected to be both caps here, same value, 680 picofarad, so I'm going to substitute, and then we get square root of R1 R2, or basically R1 times R2 equal to 1 over C square omega n square, which is computable. So knowing that, let's say, C is 680 picofarad, or basically 10 to the power minus 12 farad, and knowing omega n is some desired value, 2 pi, let's say some frequency, I don't know, I mean, example 20 kilohertz, if you like the f1, so this one is 2 pi times f1. So if you want f1 corresponding to this node to be 20 kilohertz, then that's the choice. So this one is just 2 pi f1, in which f1 is just, let's say as an example, 20 kilohertz if you like. Then with this we have the definition of R1 R2, so we know that, and we also know that R1 is 2 times R2, so we can find the value. So substituting let's say these guys, we can get basically, let's say 2 times R2 square equal to 1 over C square omega n square, and therefore R2 is 1 over C omega n and then the rad 2. So that's how we find R2, and then we find R1 as well. R1 is twice that, of course, so rad 2 omega n C times omega n. So this is how we find the value of the components in this circuit. We can do the same thing for the second stage, which with the same analysis we can quickly find the value of the transfer function. So it would be exactly same type of analysis, except wiring of components are different. Instead of having 2 caps like this, now we have 2 resistors like this. Instead of having R1 and R2 like this, now we have C1 and C2. So it's as if we just swap let's say the placement for resistors and capacitors from first stage in the first stage to get to the second stage. That's exactly what happens if we do the same analysis I did. So I'm going to write it here. So for the second stage, so for the second stage in the cascade, which is a low-pass filter, Sallen-Key filter, Sallen-Key low-pass filter in the form of a Sallen-Key topology, then what we get, if we perform same analysis, so H2S, which is the transfer function of second stage, which is output of the circuit, the final output, divided by the midpoint voltage, so it would be V out over Vm, equal to, we will find it's a low pass, and we will find it's going to be omega n squared. So in the case of, let's say, the first stage, we found s squared divided by these guys. So the nice thing is we end up with the same definition for denominator, but the values are different. So we will end up to find that the values looks like this. So omega n is 1 over, in this case, note that we have same resistor R used in the circuit instead of same cap. Now we have same resistor R, which is, for example, selected to be 4.7 kilo ohm. We have C1 here and we have C2 here. So with that in mind, if you compute and use the same method that I applied, you will find that omega n for the second stage, omega n2, is going to be 1 over R square root of C1 C2. And then you will find that zeta here, or damping factor, will be equal to rad. So in this case, it's going to be C1 over C2. So previously was, for the stage 1, the zeta was rad R2 over R1. Here is rad C1 over C2. So now it's the same idea. So this is for the second stage, and same idea, meaning that setting again zeta of 1 over rad 2 to have a flat response in the passband, we end up with Butterworth Sallen-Key low-pass filter. Let's say LPF, and so substituting S with j omega, then H2 omega squared will look like exactly as we expect from a Butterworth filter. So it will look like 1 over 1 plus omega divided by omega n, this one omega n2 for the second stage, to the power 4. And that 4 is again 2 times n. N is the order, which is 2. So it's a second order Butterworth, let's say, Sallen-Key low-pass filter. Okay, so same idea. So with setting zeta to slightly under damp 1 over square root of 2, and by selecting omega n2, which is exactly the target value for the second 3 dB drop. So remember, these frequencies are 3 dB point. We have 3 dB drop at these frequencies, so effectively they define the bandwidth. So with that in mind, we have by same idea. So by setting zeta 1 over rad 2, we are enforcing C2 to be twice C1 to satisfy and get this one. So this resulting C2 to be 2 times C1. So that's one relationship, one equation. And by forcing omega, the other one was 1. Now we get omega, let's say n2 equal to 1 over r rad C1 C2. We get, let's say, C1 C2 equal to 1 over r square omega n square. And therefore, same idea. If resistor is set to be 4.7 kilo ohm, then we have, let's say, with R given or selected, let's say 4.7 kilo ohm, if that's the case, then with the second frequency, the frequency corresponding to this omega 2. So if omega 2 is set to, say, 2 pi f2, and is f2 is selected, so chosen or given, so f2 given for a target application, f1 given, as we discussed, then we can say with f2, or basically omega n2 equal to 2 pi f2, with f2 given, then we have omega n2, which means then we have the value of the product of C1, C2. So hence, same as before, we can just say we can find basically C1, C2 as before. And we are realizing, as I said, the Butterworth transfer function. So we can find C1 and C2. As an example, if, for instance, we select, so we need to satisfy these requirements. These are super important. So C2 has to be twice C1, and to get the smooth and very flat, let's say, passband. So we need these requirements. And also, we need to get the proper value of, let's say, omega n1 and omega n2, which means the value of these guys. So let's say, as an example, if we set the values of these, so these guys are known, 680 picofarad. If we set, let's say, R1 equal to, as an example, I have example here. So let's say if we select R1 to be equal to, say, 10 kilo ohm, and R2 equal to, for example, 5 kilo ohm or 4.7, which is very close practically, so we can practically implement it. And then R here, let's say, equal to 4.7 kilo ohm, and naturally this one is also 4.7 kilo ohm. And let's say if we set the value of, and these caps are 680 picofarad. So C1, if we set it to equal to, say, 100 picofarad, and let's say as a result, because C2 has to be twice C1, so C2 has to be naturally 200 picofarad. So then what is the value we're gonna get? So if that is the case, the value we get for the first filter, the first stage here, we get, let me use a different color, so it will be equal to 1 over, of course, C is now, as selected beforehand, 680 picofarad, so we get 1 over 680 10 to the power minus 12, and square root of R1 R2, because we have the same, we have R1 twice R2, we're gonna get just 5k times square root of 2, so it would be 5 10 to the 3 and then square root of 2. If we compute this value, so I can quickly do that so that we have a reference point as just an example. So we get, let's say, let me just make sure that I'm computing it right. So we have, let's say, 680, so 680, and then we have, let's say, I think it's going to be on the order of 20 kilohertz. That's what I recall. So we can compute that. Let me just leave it to audience to just compute this. But basically, let's say if maybe I do it quickly. So this one is roughly, let's say, for this one here we have roughly 10 to the 3 and 10 to the negative 12 becomes 10 to the 9, and then we have let's say 5 times 7 roughly, we get 3,400, and then rad 2. So I think it's going to be on the order of, let's say, 10 to the, if this is 10 to the 5, 10 to the 4, then we get 10 to the 5 divided by, so it's roughly on the order of, I think, 20 kilohertz, roughly. Not exactly, but on that order. So all I'm trying to say is with the components I just showed you, we are realizing the first frequency F1 here to be on the order of 20 kilohertz. I'm not saying it's a good example. I'm just saying that you end up with whatever value you want based on the selected components, or vice versa. And if we select these components for the second stage, omega 2 roughly turns out to be about 9 times or 10 times what is computed for omega 1. So this one will turn out to be something on the order of 150 to 200 kilohertz. So depend on what we want, we can realize narrower or wider bandwidth for this filter as we wish. Okay, I hope that this example is helpful in terms of illustrating how there are many ways to design a bandpass filter. This is not the only way, but the nice thing about this method is the flexibility it brings. And if we use, for example, 2 op-amps from the same package, let's say from Analog Devices or Texas Instruments, that they offer dual op-amp packages or even quad op-amp packages, we can use same op-amps inside one package, so they are matched very well. And of course, if they are, let's say, FET input or FET transistor, field effect transistor input, then the leakage current would be very low, so low offset, low noise, and let's say good gain bandwidth for the op-amp, either from Analog Devices or Texas Instrument. We can have a very stable and flat response for the circuit inside the bandwidth, inside the in-band, let's say, frequency for the bandpass filter. I hope that this example is helpful, and it shows how the circuit is working and how components can be selected. Thanks for watching.